First one is river crossing. They're both the same type, but I'll give you an example of each, okay? And then another one is, I should probably call it two. Airplane navigation. They're typically ones like this. And I'm just going to pick an example of a river crossing one, and then I'll pick an airplane navigation one, but there'll be slightly different questions, okay? The river crossing one that I want to take a look at is where you get blown off course. By the current. And airplane navigation is where you must compensate for the air current in order to land at your target. And they're similar questions, but there's just a difference in hypotenuse. We're going to look at examples that are most common in Physics 12 in that they've got 90-degree angles, okay? So we're not going to bring sine law or cosine law into these examples, and most of the time they won't. In fact, I can't think of an example, including my final exam, where I would. So we'll be looking at very simple vectors where we've got a 90-degree angle, okay? First one, the river crossing. In the river crossing problem, it used to be quite common for us to consider the Albion Ferry and go across to Fort Langley. And Fort Langley would be right here. Actually, I'll draw it the way it should be. North, east, south, and west. Fort Langley would be right here. And Albion would be right here. And some of you, I'm sure, fondly remember going on that ferry with your families for a day trip. And we'll assume that there's a current downstream that's fairly big. The tide's out and the river is flowing, and it's spring, for instance, and we've got 8 km/h current. Okay, here's the question. Ferry heads from Albion toward Fort Langley. The ferry's speed in the water is, we'll say, 12 km/h. Speed in the water. The speed of the water, also called the current, is 8 km/h. If the captain did not consider the current then angle off course is the ferry traveling, and B, what is the resultant velocity of the ferry. And the resultant velocity means what is the ferry's velocity relative to someone on shore. So if you're on shore, what does it look like the ferry's doing? Okay, so this ferry is going to get blown off course. It's just the way it is. So we've got a boat, and the boat can travel 12 kilometers per hour in the water. So it can go 12 kilometers per hour in the water, but the water itself travels 8 kilometers per hour. The pilot or captain thought he was going to Albion, or from Albion to Fort Langley, thought he was going to Fort Langley at 12 kilometers per hour, not compensating for the current. The current pulled him downstream, and in fact, he goes a little bit faster than 12 kilometers per hour because he's really doing this hypotenuse here. So it's the speed of the ferry in the water, also called speed of the ferry relative to the water, plus the speed of the water, and that's also called the speed of the water relative to the land. And that gives you the true velocity of the boat. He's off course and going faster than the 12 kilometers per hour because the eight's adding on to it. Okay? So this is the VR, the resultant vector or resultant velocity. Here's the angle we're looking for. Right here. That'll be the angle off course that he is. So we've got everything we need. There's a 90-degree angle, which is great. So moving off of this diagram, now we just have to find out what all of this stuff is. 90-degree angle right here, right? Assuming that Albion is directly north of Fort Langley. Okay, ready? So the angle off course. I've got a nice triangle that looked like this. Theta, VR, 12, 8, and 90 degrees. And I have to find the theta angle. What is the off-course angle? So easiest way, opposite, adjacent, hypotenuse. And TOA, tan, opposite over adjacent. So tan theta is equal to opposite over adjacent. So tan theta is equal to 12 over 8. So theta is equal to, if you guys can crank it out, let me know, that'd be great. Pardon me? Would it be 12 over 8, thank you. Opposite over adjacent, yes, thank you. And you got, sorry? 0.6666. Is that what you got? Is it 6666? Okay. And going more digits, and that's tan theta. And then you got theta as being 32.7? 33.7. Thank you very much. Okay, finally got it worked out in my mind. So 33.7 degrees, it's not going south, although he thought he was. He thought he was going south. He's actually going west of south. So not south, but west of south. And that's the way you report it, okay? So he thought he was going south, but he's actually going west of south. Yeah, you can't call it southwest. Good point. Because southwest, by definition, means 45 degrees. Exactly right in the middle. So if you said southwest, that would mean this angle here is 45 degrees.
Southwest-ish.
Yeah, southwest-ish might sound okay, but it's not quite as exact as this. Okay. Okay, last part. We have to find the VR, and the VR is no sweat. It's just using Pythagoras. To get VR. And it's just hypotenuse squared. H squared equals a squared plus b squared. So whatever it turns out to be. 8 squared plus 12 squared. And what do you guys get h to be?
14.4.
Nice. 14.4? Great. And that's in kilometers per hour. So your answer really is the speed of the boat, velocity of the boat, is 14.4 kilometers per hour at 33.7 degrees west of south. Okay? So that's how you'd solve that one. There are all other questions that they could ask you. They could say, given this diagram right here, and the fact that the river is, who knows, a kilometer wide, how long would it take to go to the other side? How far downstream would they be? But it's all related to the same question. Okay, thanks.